Okay, now we proceed to the second subtopic, Faraday's law and Lenz's law. Now, in figure 20.4, okay, this shows another simple experiment to show that how changing flux can produce induced current. Okay, so in figure 20.4a, okay, we have, okay, wait, all right. So we have magnet. Okay, magnet to move towards a coil. Okay, towards a coil. Okay, the coil or the loop, okay, is connected to an emitter. Emitter will read the induced current. All right. So what happens is that when the magnet is moving toward the loop of wire, right, what happens is that there will be flux entering the loop. All right. So before there is no flux. Okay. After when we move the magnet towards it, okay, there will be flux. All right. So there is change in flux here from zero to flux. Okay. So we are reading at the ammeter. Okay. B at diagram B 20.4b, when the magnet is placed stationary in the loop, there is no current, no reading of the ammeter. Okay, in diagram C, when we move the magnet away from the loop, right, away from the loop, there will be also a change in flux. Okay, from more flux to zero flux when we move it away from the loop. All right, so there is a reading of the current, but in the opposite direction, as in A. All right. Let's go through Faraday's law first before we proceed to more detail about Lenz's law. All right. So Faraday's law of magnetic induction states that, okay, the induced EMF produced is directly proportional to the number of turns of the loop. Okay, and is inversely proportional to the interval time during the change of flux. Meaning, to get the induced EMF, to get the most value of induced EMF, it must occur at a very short time. All right. Now, the negative sign indicates Lenz's law that shows the direction of the induced current. All right. Now, when we substitute the equation of magnetic flux inside Faraday's law, where we know that the flux is given by, okay, pi equals to B A cos theta. We substitute into here. We can see that induced EMF can be produced by changing the magnetic field. Okay, or we can also produce induced EMF by changing the surface area. Okay, or we can also produce induced EMF, okay, by changing the rotation, okay, or sorry, by changing the angle theta here, okay, meaning that changing theta means we rotate the plane, okay, in other direction. All right. So in this chapter, we just consider two ways, okay, to produce induced EMF by changing magnetic field and by changing the area. We are going to skip the third method here. Okay. So let's learn more detail about Lenz's law. All right. So what is Lenz's law? It says that the current caused by the induced EMF travels in the direction that creates a magnetic field with flux opposing the change in the original flux. Okay, what does it mean? Okay, we know that as we move the magnet, okay, towards the loop, what happens is that there will be change in flux at the loop, isn't it? All right, from zero to a certain value of flux, right? So the change in flux will produce induced current at the loop. So the induced current itself also creates, okay, its own flux, a new flux, okay. So since the new flux will oppose the direction of the original flux, okay. So you can see that the flux of the magnet is coming towards the loop. All right. So the induced current will create flux in the opposite direction, like this. Okay, in the opposite direction. All right. So it will be like this. All right. So to find the direction of the current, we use right hand rule number 2. All right. So you curl your 4 fingers, okay, to the according to the direction of the new flux. Okay. Uh, at the entire loop. Alright, so you get like this. So the current will be pointing downward. You curl your forefingers so that it will be like this. Alright, in that direction. So your thumb is automatically directed downward. Alright. So for the next diagram, okay, you have steady flux, okay, to the loop. Okay, steady flux, so there's no change in flux. So the reading will be equal to, the reading from the ammeter is 0. Okay, next, what happens when we push the magnet away from the loop? All right, so there will be decreasing in flux. Okay, according to Lenz's law. Okay, basically for Lenz's law dia tak nak sebarang perubahan. Okay, meaning if the flux decrease, dia akan increase balik. Alright, so there will be dia nak stable balik lah keadaan flux ni. Alright, so when flux decrease, Lenz's law akan cuba tambah balik. Right, so how? Okay, the induced current here will create a flux with the same directions, but dia tambah balik, dia akan create with same direction. So the flux will be like this. Alright, same direction. Alright, same direction like this. So you curl your forefingers like that. Right, you curl your forefingers with the same direction as macam ni. Okay. So the induced current will be directed upward. Okay, another example of Lenz's law. Right. So let's say we have a current, okay, of a current travels through a wire, okay, to a straight wire, long straight wire. Okay, and let's say the current increase with time. The current increase with time, and we have a rectangular loop beside the wire, right? Now we know that from previous chapter, a wire that carries current can produce its own magnetic field, right? So you can see that the magnetic field here is counterclockwise, right? Now, when the current increase, meaning there is more flux. Okay, there is more flux here, isn't it? Okay, and there is the left side of the rectangular loop. Okay, so what happened? Okay, the rectangular loop will produce induced current because of the change in flux here. Okay, the rectangular loop will produce induced current, and the induced current here, okay, will set a new flux. Okay, a new flux which will oppose, okay, the original flux, right? So we just look at the center of the rectangular loop here because the flux is greater at the center. All right, so at the center the original flux seems to be into the pitch. All right, so the new flux set by the induced current would be out of the pitch. As you can see here, is out of the pitch. All right, out of the pitch. Okay, so how to find the direction of the induced current? By using right hand rule number 2. So this will be counterclockwise, and the direction of the induced current will be up, okay, at this side. All right. Okay, here is another example applying Lenz's law. Alright, so in figure 20.9a, we have a magnet that is moving to the right, okay, to the coil. Alright, so what happens is that there will be more flux entering the coil. As the magnet is moving toward the coil, there will be more flux entering the coil. Right, so according to Lenz's law, alright, according to Faraday's law first, okay, because of the change of the flux, okay, is becoming more flux, okay, toward the coil, so there will be induced current, okay, at the coil. Now we apply Lenz's law. All right, the induced current here will create a new flux that will oppose the direction of the original flux. All right, so the induced current will will set a new flux that will be in the opposite direction like this. All right, so you curl your forefingers, okay, follow the direction of the flux that is created by the induced current, so your thumb will be directed upward. All right, so at the top of the loop it will be like this. All right, so you just curl your forefingers, okay, according to the according to the new flux created by the induced current. All right,